My name is Jeroen van der Donckt and I'm going to present our technical paper. We first introduce the overview. In the first section, we will talk about the setting. There, I will elaborate on self-adaptation, the evaluation case, adaptation goals, and the adaptation space. Then, I present the challenges coupled to verification of large adaptation spaces, which will be followed by the research goal. Next, we introduce our approach named DLASER, and then we present the evaluation results. Finally, we conclude and discuss future work. So first we start off with the setting. Our work is situated in the domain of self-adaptive systems. Such systems are actually a software system that consists out of two parts. On the one hand, you have the managed system. That part is subject to adaptation. On the other hand, you have the managing system. This can be seen as a system that is placed above the managed system and manages that managed system. So self-adaptive systems are deployed in uncertain environments, meaning that they should work under changing operating conditions. These uncertainties are highlighted in red, meaning that we need to cope with this as a challenge. Adaptation options or means to adapt the self-adaptive system are certain configurations or parameters of the managed system, and adaptation itself is guided by the adaptation goals. We apply adaptation to realize some certain quality of service for applications that require business continuity. Concretely, we position our work in the MAPE-K architecture-based self-adaptation. In this figure we see two parts as mentioned before. We see the managing system on top of the managed system. In this case the managed system is an IT system. The 5 MAPE-K components are the monitor, the analyzer, the planner and the executor, which all share a common knowledge. The monitor monitors the system and its environment. The analyzer analyzes the monitored results or values and decides whether adaptation is required or not. To that end, it uses a verifier. Then the planner selects the best adaptation option and creates a plan for it. And finally, the executor executes that plan. We highlighted analyzer and verifier because these are two components that are quite important in our work. So we will zoom more into these in the rest of the presentation. Now, the evaluation case that we used is the Delta IT Internet of Things setup. We used two instances of the setup containing 15 and 37 modes. The real-world deployment of this IT setup is at the Arenberg 3 campus at Leuven University. The IT network consists out of 3 types of sensors. You have RFID sensors, you have passive infrared sensors and heat sensors. Each mode is battery powered and the parameters or the configurations that can be altered are the power setting and the load distribution. So these are the 2 things that can be changed to adapt the system. And these are both on the level of each mode or the links. The power setting is for each mode and the load distribution is on each link between the modes. And the qualities in which we are interested are the packet loss, the latency and the energy consumption. Now we've come to what is an adaptation goal. An adaptation goal is a goal defined for the qualities that are subject to adaptation. So in the case of Delta IT, these 3 qualities were energy consumption, latency and packet loss. A violation of such a goal will result in an adaptation action in the hope of, again, restoring the goal. We will focus on 2 types of goals. We will focus on threshold goals, which states that a quality should stay below or above a given threshold value, and an optimization goal, which states that some quality should be minimized or maximized. So here we show a toy example. We consider 2 qualities of the Delta IT evaluation case. Concretely, we consider the latency and the packet loss. So now we've come to what is an adaptation space. An adaptation space is a set or a collection of adaptation options, where an adaptation option, as said before, is a configuration or a parameter setting. Such an adaptation space is subject to dynamic behavior. This means that the qualities of certain adaptation options, or even most adaptation options, change over sequential adaptation cycles due to changes in the environment, but also due to changes in the configuration of the self-adaptive system. To tackle this, a common way to tackle this dynamic behavior is to use verification. And here in the figure we actually show the dynamic behavior for delta IT. We consider the three qualities and display the verified quality of a certain adaptation option over 50 sequential cycles, and we can clearly observe that it's never clearly the same. So this is a proper indication of this dynamic behavior. And specifically for delta IT, the smaller instance has 216 adaptation options, whereas the larger instance contains 4096 adaptation options. Now we present the challenge. The problem this research tackles is that exhaustively analyzing the full adaptation space is both time and resource consuming, meaning that it might be infeasible for large adaptation spaces to do this. But on the other hand, doing such an exhaustive analysis ensures guarantees that are either exact or statistical depending on the specific type of verifier that is used. So the challenge, which makes this problem quite hard, is first of all the dynamic behavior of the adaptation space, and secondly that we have limited time for analysis or verification. Thus, what we want to achieve is a fast analysis which enables us to react quickly to changes at runtime. This leads to the following research goal: how to reduce large adaptation spaces of self-adaptive systems with multiple threshold goals and an optimization goal effectively. With effectively we mean 5 things. First, we want that the reduced adaptation space is significantly smaller. Second, high performance. With this, we want to indicate that the reduced adaptation space covers the relevant adaptation options well. 3, we want a minor overhead. We want that our approach results in little to no additional time. 4, the effect of the state space reduction on the realization of adaptation goals should be neglectable. And 5, we want that our solution is scalable, meaning that we want to observe no notable effect on the 4 aspects above when we scale up to a larger adaptation space. To capture each of the aspects of the research goal, we defined or we used appropriate metrics. To capture the reduction of the adaptation space, we used the average adaptation space reduction metric. This is the micro average of the reduction of the adaptation space over multiple adaptation cycles. To capture the performance, we used the F1 score for the threshold goals and the Spearman's row rank correlation for optimization goals. The overhead will be indicated by the learning time that our learning solution required. And the effect on the realization of goals will be researched by means of the mean values, that is actually the distribution observed through box plots from our solution compared to a reference approach. And finally, for the 5th aspect, we will look at the 4 aspects above, but then for a larger instance. Now we've come to our approach named DLASER. DLASER stands for Deep Learning for Adaptation Space Reduction. Our approach is composed out of 2 stages. In the first stage, we tune the hyperparameters on offline collected data. And in the second stage, we deploy the models in an adaptation environment and use online learning to perform adaptation space reduction. Our approach tackles multiple threshold goals and 1 optimization goal. We focus just on 1 optimization goal, as handling multi-optimization goals would result in some Pareto optimality, which we consider out of scope of our work. We verify the reduced adaptation space for threshold goals or optimization goals and also add an exploration rate. This exploration rate corresponds to some certain percentage of unselected adaptation options that will be verified to capture a good representation of the full adaptation space. These results will be used by the learning models to update themselves to adapt to the uncertainties or the shift in the adaptation space that is actually the dynamic behavior. Then one might question why we use deep learning in self-adaptive systems. First of all, given the success in many other areas, and also the fact that deep learning requires no feature engineering, which makes applicability in practice considerably easier. So our DLASER solution, as said before, is composed out of two stages. In the first stage, which we call the offline stage, we first collect data. This data is split in a training set and a validation set, and the data itself is composed out of feature vectors, which is information about the system, and adaptation options and qualities, which are the qualities of the system in which we are interested. For each goal, we will train a deep learning model. Therefore, we apply a grid search process to obtain the hyperparameters of the model and the scalar. This grid search process is guided by the metrics we defined in advance, and the output of this process is a deep learning model and scalar for each goal. Once we have obtained this, we continue to the online stage. In the online stage, we make a difference between two cycles. We have the training cycle and the learning cycle. In this online stage, the models are deployed at runtime in the system, and in the training cycle, the models are initialized to the current environment. To that end, the scalar and the model is fit to the features of the system. In the succeeding learning cycles, the models are utilized to perform adaptation space reduction. Each model predicts on the transformed features. The next slide elaborates on how to utilize this prediction for effective analysis, and the analysis results of either the reduced adaptation space and also the exploration rate will be used to update the models themselves. So now we indicate how the adaptation space is reduced for threshold goals. We online learn which option will satisfy the threshold goal, and the specific mechanism or technique that is used is binary classification. For each threshold goal, we will have a corresponding deep learning model that learns whether or not an adaptation option will satisfy the threshold goal. So here in this example, we present the adaptation space of delta ITV1, which is a smaller instance of the evaluation case. We have two threshold goals. The latency should be below 5% and the packet loss below 10%. The orange dots are the ones that are predicted by both deep learning models to satisfy the threshold goals. So this is the intersection of the predictions of both models, and the blue ones are the ones that are predicted to not satisfy the threshold goals. And in order to tackle an optimization goal, we rank the adaptation options by means of the regressed values. So for the optimization goal, we maintain a regression deep neural network. Here, the ranking is used to perform or to enhance the decision making or the analysis process in self-adaptive systems. So now we show how both are combined. This slide shows how the predictions of the threshold goals and optimization goals can be combined. We first perform the threshold stage, which will be followed by the optimization stage. For the threshold goals, the reduced adaptation space corresponds to the predicted subset of adaptation options for all goals. If there is no optimization goal, we will just verify all options of this predicted subspace or of this reduced adaptation space. If there is an optimization goal, we will continue to the second stage, which is the optimization stage. There, we will verify the ranked adaptation space, the ranked subset actually of the adaptation space, and we will do this until a verified option is found that satisfies all the threshold goals. So in this stage, the order determined by the regressed values from which we infer a ranking is really important, since this will speed up or enhance the verification process. So here we have an illustration of how these two stages work. On the left we have the set of adaptation options, that is the adaptation space. Each gray dot corresponds to an adaptation option. In the first stage we consider two threshold goals. We classify and reduce the adaptation space for the first threshold goal, so the green dots are the adaptation options that satisfy the first threshold goal. Then for the second threshold goal we predict and classify this again for the reduced dots based on the first threshold goal. And then we pass the valid threshold goals, which corresponds to the intersection of both threshold goals, to the optimization stage. And in this optimization stage we regress and verify the adaptation options in ranked order. Now we've come to the evaluation of the DLASER approach. To that end we use the .it simulator. We use the simulator for practical reasons. The adaptation goals we considered for evaluations are two threshold goals and one optimization goals. The two threshold goals are respectively T1 and T2. The first threshold goal states that the average spectral loss should not exceed 10%, whereas the second threshold goal states that the latency should not exceed 5% of the cycle time, and the optimization goal states that the average energy consumption should be minimized. So now we give an illustration of the adaptation space. This is the adaptation space of .itv2, which is the larger instance with 4096 adaptation options. Each blue dot corresponds to an adaptation option, and the red lines indicate the two threshold goals. And for .itv1 we were even able to obtain a proper 3D visualization of the adaptation space. So the gray box indicates again the feasible region according to the two threshold goals, and the red dots correspond to the adaptation options that are within this feasible region. We have come now to the evaluation of our work. We compare our work with previous work that utilized classical machine learning and evaluated the same two instances with the similar or with the same goals as we did. To capture the reduced adaptation space, we utilized the average adaptation space reduction metric, and we observed that for the two threshold goals we obtain a significantly higher average adaptation space reduction, and this is only for the two threshold goals. So when we incorporate the optimization goal that is used for the decision making into our DLASER framework, we see that we obtain an even higher average adaptation space reduction. Now we look at the performance. To that end we utilize the F1 score for the threshold goals and the Spearman rho for the optimization goal. We see that the F1 score is very similar to the previous work with only less than 0.1% difference. And for the Spearman rho rank correlation, we see that there's a large decrease from 80.2% for .itv1 to 25 or 24.5% for .itv2. One might think that this would result in significantly inferior results, but further analysis or further results will show that this is not specifically the case. When we look at the overhead, we consider the learning time. For .itv1 we observe that the learning time is smaller than 0.5 seconds, and for .itv2 the learning time is less than 1 second. We observe the obvious trend that the learning time increases with increasing number of adaptation goals. This is as expected, as we used one deep learning model for each adaptation goal. I would say that this increase is rather linearly. When we look at the time fraction, that is the fraction of learning time compared to the verification time, we see that the previous work described or observed a time fraction of less than 1%, whereas our approach has a very small time fraction for .itv2 and a fraction that is somewhat higher than 1% for .itv1. So this states that deep learning has a minor overhead when the adaptation space is not very large, but a considerable or neglectable overhead when the adaptation option is rather large. Next, we look at the effect on the realization of the adaptation goals. We compare the DLASER framework with a reference approach that verifies all adaptation options. For the two threshold goals, that is packet loss and latency, we see that they are both always satisfied by the DLASER framework. And as for the optimization goal, that is energy consumption, we see that we obtain a small increase for the DLASER framework in favor of a large adaptation space reduction. When we look at the larger instance of data IT, we see again that both threshold goals are always satisfied, but for the optimization goal compared to the reference approach, we see that we now obtain a significantly higher energy consumption. This is roughly 1.2% higher. This energy consumption, this small increase in energy consumption is in favor of a large adaptation space reduction. Note that the verification of all adaptation options, as has been done for the reference approach, is not feasible in practice since the verification time exceeds the adaptation cycle time. Now, with this slide, I want to indicate how the dynamic behavior is tackled by means of online learning. So this represents the adaptation space at some certain cycle. So this is the succeeding cycle, and there's a considerable shift in the adaptation space, yet our models by means of online learning captured this shift very well, which indicates that online learning is a useful practice or manner to tackle this adaptation space problem. Finally, we have come to the conclusion. By means of the evaluation results in the previous slides, you are able to answer each aspect of the research goal. In order to answer this significantly or to make statements about the significantly smaller adaptation space, we used the average adaptation space reduction metric. We observed that we obtained excellent adaptation space reductions nearing to optimal possible values. As for the performance, we used the F1 score for the threshold goals, which was an overall excellent, and the Spearman row was okay. It was great for the smaller instance, but we noticed a significant or a large decrease for the larger data IT instance. As for the overhead, we used the learning time and the time fraction. We observed that the time fraction decreased with increasing adaptation space. For the effect on the realization of goals, we observed that the threshold goals were always satisfied for both instances, but the optimization goal was slightly compromised in favor of a large adaptation space reduction, yet this compromisation was quite small. It was less than 1.2% for the larger adaptation space. So in overall, we observed no major differences when scaling up from the smaller setting to the larger adaptation space. To conclude, we focused on analysis in large-scale self-adaptive systems. This task can be infeasible for large adaptation spaces. Adaptation space reduction is one possible manner to handle this. Our proposed approach, named DLASER, tackles multiple threshold goals and or one optimization goal. The tool we used is online deep learning. We used one model for each goal, which required one grid search process in the offline part of the learning pipeline. And our results indicated that we obtained a significant more effective adaptation space reduction than previous work, with minimal loss in qualities and with little to no overhead. As for future work, we will present in the near future DLASER Plus, which is the next iteration of this DLASER framework. In this framework, we will tackle multiple threshold, multiple set point, and one optimization goal. Again, the tool will be online deep learning, but now we will have one deep learning architecture for all the goals, which enables or which makes it necessary to predict only once, which will also result in only one grid search process instead of one grid search process for each goal. And in general, we want to evaluate our adaptation space reduction approaches beyond the domain of IoT. We want to tackle, or we plan to tackle multi-optimization, and we want to research the effect or the ability to dynamically add and remove adaptation goals. Thank you for your attention.